So in this video, we'll look at how to integrate the rational functions where the degree at the top is at least the same as the degree at the bottom. So please recall that in all the videos we have seen in this topic of rational functions, we have never dealt with this case. So you see previously we looked at the case A. I've been calling it case A in the previous videos, where the denominator always has a higher degree than the top. But we have never seen a case where we actually have the degree at the top at least the same as the degree at the bottom. So in this video, we'll indicate how we can deal with this case in this video. And surprisingly, all the methods we learned about this partial fraction decomposition for the case A still applies to our current case B. But you need to carry out a new process to transform the case B where the top has a higher degree than the bottom. You have to transform it back to the case A, which means there's a method you need to learn to make the degree at the top lower than the degree in the bottom. Then after that, you can still carry out the methods we learned, right, about the partial fraction method and integration, etc. So we'll try to look at a problem now. So please look at the current problem. Let's check the degree first. You see the top actually has a higher degree than the bottom. So please, you cannot start the partial fraction decomposition now when the top has a higher degree. So what you need to do is actually a classical method. I believe all of us have learned this, which is called long division. In arithmetics, everybody have seen something like that. For example, if you're given 12 divided by 5, and in the elementary school, we have seen something like the division method, and now we have to apply the division method to our current case where we actually have the polynomials instead of numbers. Let's see how to do it. You have to put the top of the fraction inside this symbol, the division sign. And it is my intention to leave out some space between the x power 4 and plus 1 because we actually don't have the term x cubed, x squared, and x. So these are the terms that I leave out in the middle. So anyway, outside the division sign, we need to put in the denominator, which is x squared minus 2x minus 3, right? And now, to finish this division process, you have to just look at the largest power every time. So this time, you are just checking out the largest power, which is x to the power 4 inside, divided by x squared. And we understand that, I mean, x power 4 divided by x squared is just x squared. So we have to put in the x squared at the top because of this. And this step is a typical division step. You need to multiply this x squared, the multiple, with the whole thing in the divisor, right? And after multiplication, x squared multiplied with the whole polynomial, we actually have x power 4 minus 2x cubed minus 3x squared, right? And this minus sign outside means that you have to look at the polynomial in the first line minus the polynomial you have in the second line here. So after the subtraction, of course, this part is 0. You see, there's nothing. It is 0. X power 4 minus x power 4 is 0. The next term is going to be minus 2x cubed, which is plus 2x cubed. And similarly, the next term is going to be plus 3x squared. And the last bit, we have to bring it down, which is plus 1. So that's what you have for now. And then you have to keep doing this process until the remainder, which is this line, has a lower power than what you have in the divisor. So we have to continue because now the remainder still have the power 3. And we have to use the highest power, 2x cubed, it is divided by x squared, so which is 2x, which means the top as a multiple is 2x. And the next step is similar. You have to put a minus sign in front, and you have to use the 2x in the multiple to be multiplied to the whole polynomial as the divisor. So after the multiplication, we have 2x cubed minus 4x squared minus 6x. You see, every time I use this process, you have to align the power in the same column. And now this part is gone, right? Because you are using minus in the middle, which means 2x cubed minus 2x cubed is gone. And for the next one, it is 3x squared minus 4x squared, right? It becomes 7x squared. And similarly, this term becomes plus 6x because it's minus in front, and then minus 6x, right? And plus 1, you have to keep it there. And should we continue this process? The answer is yes, because you see the power now is is at least still the same as the divisor. We want the power in the remainder to be less than the largest power in the divisor we want. So we have to keep going maybe at least for one more step. And here you see, once again, you have to compare the highest power, which is 7x squared, divided by the highest power in the divisor, which is x squared. So it becomes 7. So the next multiple is 7, right? And then you need to use 7 to multiply to the whole divisor. I mean, to get the second line here, 7 times the whole thing in the divisor. So it becomes 7x squared minus 14x minus 21. And you see, this term is gone, which means we don't have the x squared term anymore in the remainder. And for the next term, it's going to be 6x minus 14x. It becomes 20x, right? And for the last term, it's similar. It's 1 minus 21, which is 22. And this one is our remainder. So basically, the division process is complete when the remainder has a lower degree than the divisor up here. So anyway, it means what? After the division process, we understand that for the integration of the rational function I put in the left-hand side of the equation, it can be written as the multiple, which is the top, x squared plus 2x plus 7, plus the remainder now, which has a lower degree than the denominator, 20x plus 22 at the top, divided by the divisor, which is x squared minus 2x minus 3, right? So it means originally, you are asked to integrate the left-hand side. Equivalently, now you can integrate the right-hand side, which is good, because this term we are guaranteed to have a lower degree at the top than the degree in the denominator. And let's write down the calculation now. So please check out this calculation. For the multiple, it is so simple because we can get the answer just by the power rule. So I can write the answer down here by the use of the power rule. And please notice that to integrate this one, you definitely know how to do it because we have learned it for quite a few videos already. Now you check the degree. The top has a lower degree than the bottom, and which means that we can start the partial fraction decomposition after we factorize the denominator. Now the factorization of the denominator is easy because it's x minus 3 times x plus 1, right? It means that we need to use the partial fraction now. So in case if you do the calculation correctly, you should be getting what I'm having here. So please note that you have to write this step down correctly after canceling the denominator. And you just have to choose the x be minus 1 and x to be the same as x equals 3 to solve for the constant for b and a respectively. So anyway, it means that you are left with, for this integral on the last bit, you just have to integrate a, which is 19 over 2 divided by x minus 3 plus 21 over 2 divided by x plus 1. And of course, because both factors are degree 1, you can write the answer down pretty quickly, right? So because for degree 1 factor in the denominator, we can just use the lump function. And it means that we can just put this answer, the last two parts here, back to our answer in the black color in the first line. So it means the final answer is the following. So you see, it's basically our final answer to the huge problem here. And as you can see, this process does not give you extra difficulty, apart from the fact that you have to spend more time on resolving it by using the division process first. And then you can still get the rational function, which has a lower degree at the top. And from there, you can use the partial fraction decomposition method you have learned before. So basically, that's the end of this video.